Hi, this is Larry Benko, call sign W0QE. And about 3 weeks ago, I did 2 videos on Baluns. One was titled Balun Modeling, and one was titled Balun Stresses. And while the videos were not watched by nearly as many people as some other videos have been, they generated more questions to me privately than any videos I've ever done. Which brings up the question, is the topic of interest only to a few people, and is it poorly understood? Or did I do a poor job of explaining the topic? Or perhaps something else? Nevertheless, I thought I'd do a third video and try to explain some of the questions I got, which may be of interest to a larger group of people. I've rephrased the questions. I got questions from 6 individuals. And a couple of them were very long emails with lots and lots of questions that were almost impossible to answer in an email. But fundamentally, the questions went along these lines. If I build a balun, how do I know if it's good enough when I'm done? And then there was the question about why I kept messing with the center-ground connection when I did the previous videos, and what was the purpose of that. I thought I had explained that, but I guess I didn't explain that very well. And there was, of course, questions about flux versus transmission line baluns and what's the difference and why is one better than another, etc. And then the typical voltage versus current Balun and Unen questions, which are always seem to be asked, in any time you mention baluns. Then coax versus 2-wire modeling. Do you model coax differently than you would model a pair, like open wire line? What core material should I use? And finally, this question was asked twice, and I figured this out probably 2 or 3 months ago, and it's a very interesting answer. But there are many, many people who believe that a 1-to-4 or a 4-to-1 current balun has to either have 2 cores, or some people claim it can be built with 1 core. And I believe I understand why both groups of opinions exist. And finally, why do I need a balun? Why do I want one? How do I know if I need one? And now that I have one, what do I expect that's different? These questions are obviously, I have answers to some of them. I'm not a balun expert by any means. I understand circuit theory pretty well. I understand RF pretty well. And baluns are not always the easiest things to model. So let's look at the first case. This circuit is similar to circuits I did in the previous 2 videos. But let me explain it a little bit better, and hopefully I can explain a couple of the questions, answer a few of them right here. First of all, we have a piece of transmission line. Simsmith models this piece of transmission line very specifically. It models it correctly for a differential impedance. It has an impedance if I look between these 2 terminals looking into it, and that is what we typically call the characteristic impedance or surge impedance. It has a delay that's appropriate based on the length and the velocity factor. It has a loss appropriate to, if I had chosen to put those parameters in here, or if I'd used one of the models that are provided with Simsmith for a piece of transmission line of a particular type. It does all of those things. However, there is one other characteristic of a transmission line that is not modeled in Simsmith, and that is a thing called common mode impedance. If I was to tie, say, terminals A and B together and tie C and D together and look at the impedance from A and B to C and D, or just do it from one wire to the other wire, that would be the impedance across the piece of transmission line. In Simsmith, with the transmission line model, and it's also true in LT Spice and every other simulator I've ever seen for transmission lines, the common mode impedance is modeled as an infinite number. And let's look at that just very briefly here. So I built this circuit at the end here for the load, which is nothing more effectively than a potentiometer. We've got a total resistance here labeled RT, which is 50 ohms in this case. We've got a bottom part of the resistance, which is 25. So this is a center tap on this 50 ohm resistor. If I look at the voltages necessary to drive these 2 resistors such that there is no current going to ground here, and I'll explain. This is the center tap question. I'll get to that in a minute. But if I define that I want these 2 currents to be equal and I want no current here, I have to drive this point and this point with very specific voltages with respect to ground. And let's look at those voltages. So here's the plotting choices. What I'm going to look at is voltage C to ground and voltage D to ground. So here's C to ground and here is D to ground. They're equal and out of phase because both resistors are equal. Now, what if I make the resistor here a little less? I start to see a disparity in the amplitudes of the two voltages. Go the other direction. Same thing. Now let's look at the currents in R5, R6, and R7. So I5 here is the current in R5. I6 should line up exactly on top of it. That's what we want. And then IG right here is defined to be the current in R7. And we see that that's 0. This is by definition a perfect Balun. There is no common mode current. Now, what if I make my load no longer a balanced load? My Balun changes my voltages appropriately, but no matter what I do to my voltages, I still maintain this relationship. Both the currents in these two resistances are identical, and there is no current flowing to ground. That by definition is as good as it gets. And the way that we got that was by having an infinite impedance from here to here, common mode wise. Now we know that that's not true because if we look at this circuit for a minute, this is a 1-foot piece of transmission line. Let's make it really small. Actually, let's make it 0. I believe SimSmith will not honor my request to make this 0. It'll end up being some incredibly small length, like maybe a millionth of a foot or something like that. But let's make it 0. Notice I still have the same case. It's pretty unlikely to imagine here, it's pretty unlikely to imagine that a 0-foot piece of transmission line can have an infinite impedance across it. And that's just the mathematics of doing this. So what we end up doing normally is we go 1.4 feet, just happened to be the length of what I was winding when I did a lot of my measurements. What we do is we put an impedance across here, which we define as being the common mode impedance. And what I've done here in this case is just put it on one side. I'm looking at a file. The file turns out to be the file I used before. We could go look at the file here real quickly. Oops. Kill that, sorry. And let's look at just the pink curve. What I did is I put it just here in the load, but in this case, P1 doesn't connect to anything, so these are two separate circuits. So when I look at this, and what I see is at 1 megahertz, it looks about like about 12 microhenries. And as I go up to 10 megahertz, it looks like about 13 microhenries. It has a resonant point, let's see, I'm only going in this example up to 30 megahertz. It has a resonant point, if I remember correctly, around 32 megahertz. But that's what it looks like. So with that being said, we can put that file here, and it becomes an impedance file. And that means that this common mode impedance of this piece of transmission line matches exactly what I measured it to be. So now let's look at what we get when we do this. If we go back to this other graph for a moment, now we no longer see that the common mode current is 0. Even if the load is balanced, there's still a little common mode current. As we make the load less balanced in one direction, the common mode current actually gets a little bit better. We make the load unbalanced in the other direction, the common mode current gets a little bit larger. And as I indicated in the previous video, if the common mode current is less than about 10% of the differential current, most people don't worry about it because that represents 1/100th of the power, and it's hard to get too excited over that. But nevertheless, this is more like how it really works. Now let's think about this for a minute in terms of this output structure. If I was to have a dipole in the air and I had two symmetrical pieces to the dipole, so it's clear in the air, same height on both ends, and a piece of open wire line that came down just to above the ground level. Now right there at the ground level, I would put a ground stake, and let's just say that my ground stake is perfect ground. And then I would take my little impedance analyzer and I would measure from my perfect ground point to one side of the open wire line, and I get an impedance. Then I'd measure to the other side of the open wire line, and I get an impedance. That's what these two impedances represent. There is an effective ground when we think about those two impedances as being single-ended. Now, if we measure across the line, we see a total, and the total will, the total will match exactly what our two individual measurements matched before, provided we had a point that was ground. If our point wasn't really ground, but was 10 ohms or something to ground, then we have to get rid of the 10 ohms. But what we can do here is we can look at each one of these independently and see what we have. That's why it's modeled like this. I really don't know what it is in reality, but by building something like this circuit that we're allowed to move this around, we can say to ourselves that that represents the kinds of things you would expect to see, and it's a good example of showing what the currents that are flowing in the Balun are. So what we have here at this point in time is we have a perfect piece of transmission line, no matter what the length, which is unreasonable. We put a parallel impedance on one side or on both sides. I showed in the previous video, both sides actually is a little bit better in some cases, although it's hard to get too excited over how much better it is. If I put the impedance on both sides, I have to double it, that's all, because it's two things in parallel. An interesting thing here is if I do this, and I come back and I want to measure some currents here. The current, let me get rid of everything here except for one specific thing. This is the common mode current as measured in the, let's see, what am I doing here? There we go. That's the common mode current that I measure to ground. If I measure the current in this resistor right here, coincidentally enough, bring this back up again, in the resistor R9, actually I'm measuring what's in R8 and R9, but R8 has nothing in it. So I measure R9 and we call that the common mode current. It's exactly the same. And of course, it is exactly the same as the difference in current between these two impedances. So let's measure that one also. They're all three on top of each other. First one, second one, third one. So we can call the common mode current various things. We can call it the common mode current that's in the Balun. We can call it this current that goes effectively to ground, and we can also call it the current that's the difference between the two of these currents, which they should be in a transmission line. They should be equal and out of phase, but when there's common mode current, they aren't. There's a little bit of there's a third component there. So hopefully that's helped somewhat. Now I said a minute ago that the common mode impedance in this model was infinite. I should probably show that real quickly here, and I can show that by leaving these components off. We can disconnect the output from the transmission line, and we can measure the impedance coming in here from this point to that point. Now P2 is connected across the transmission line. And if we go look at here at our plot, what we see is an infinite impedance. It's infinite impedance swept over the whole frequency range, and that's the reason why we see no common mode current until we put an artificial impedance across the transmission line. Now let's look at these four circuits. They all have a fair amount of commonality, yet they're quite a bit different. Circuit number 1 on the left contains what you would typically call the classic flux transformer. We have a winding which is connected to the generator, which is here, and we have another winding which is not coupled at all to this winding except via the core that drives the load. Again, I've used the standard convention I've been doing in the circuits where I have the ability to ground either any of these points and see the performance of the circuit. If we want to build a Balun, typically we ground the center. This side's unbalanced, this side is balanced. Balun meaning balanced, unbalanced. If you want to build like an Unan, you're talking about unbalanced to unbalanced, so you would probably connect this point to ground right here. And if you want to build some kind of an inversion device, you'd connect point A to ground. But nevertheless, this circuit transfers energy from one side of the circuit to the other almost totally from the core. The two coils are not coupled together appreciably at all. We find if we do that, what we get is a coefficient of coupling down here of 0.5 to 0.7. These were with 61 material cores. If you use cores that have higher permeability, you will find it. By the way, this core is little compared to these. They're all supposed to be the same size. It's a little drawing error on my part. But you'll find that the coefficient of coupling is 0.5 to 0.7 for 61 material. And I wound a core approximately just like this, where I had a significant portion of the core not containing windings, and I had about a fourth of the core with windings, a fourth of the core with windings, and about another half of the core with no windings. If we want to calculate the flux in this core, it's the generator voltage across this number of turns. All these circuits have 7 turns, so it'd be the generator voltage across these 7 turns. We do this, and we find out that the circuit we get probably does not make us happy. And the reason for that is the leakage inductance. With a coefficient of coupling of 0.5 to 0.7, we have a fairly large amount of leakage inductance. And the leakage inductance looks like it looks like an ideal transformer in here. Let's say it was a coefficient of coupling of 0.7. It's an ideal transformer in here, which couples 70% of it ideally. The other 30% is inductance in this lead, or whichever lead you want to use. But that 30% of the inductance is a lot of inductance, and it means that this circuit is very non-broadbanded. And we're playing with a couple of different issues here that we have to weigh against each other all the time. We need enough turns here that at the low frequency that the magnetizing inductance here doesn't give us a bad impedance from back to the generator. Yet at high frequency, we have so much inductance that the leakage inductance kills us, resulting in this circuit being fairly narrow banded. Now, we can get away, if we don't require broadbandedness, we can certainly put a capacitor in parallel with this inductor, make this impedance look much higher than it actually is in terms of its inductance alone. That will help. There's a lot of things we can do, but this circuit is typically not very broadbanded. And we may not care. If we're going to put a load out here of some sort, however we intend to use the circuit, and we have a tuner back here, it may not matter. So the typical thing that people do is they get rid of this circuit very quickly, and they go to some kind of circuit where the two coils are coupled together, not necessarily as a transmission line yet, but as they're maybe wound on top of each other, maybe they're wound nearby, maybe they're bifilar wound, but they're not. The impedance isn't really controlled. I've shown them a little bit wider than right next to each other. Again, now we drive the generator on one coil, which is the red wire to the red wire. We take the load off the other one. Now, what do we see when we do this? What we see is the coefficient of coupling rises drastically. We still have the same amount of flux in the core that we had before, as long as we have the same number of turns that we had before. But we also find out that the common mode current goes up in this circuit. This circuit does not have nearly the isolation this circuit has. This circuit had great isolation. This circuit has slightly less isolation. But maybe we're willing to trade a little bit of isolation for a higher coefficient of coupling, which gives us the ability to make this circuit more easily broadbanded. We can take that to a further conclusion. Instead of making it roughly, the two windings on top of each other, we can force them on top of each other, and I've shown that by just putting a piece of coax in there. Now, in this case, the generator drives the shield on both ends, and we take the output off from the center conductors. It could have been the other way around. It wouldn't have mattered. In this case, we have extremely good coefficient of coupling. Again, the flux in this core is exactly the same as all the others. It's just the generator voltage. Now, if the generator voltage had to rise because of the impedance on this circuit being odd to get the power to the load, that would increase the flux in this core. But if we assume that we don't have to play many games with the generator voltage, all three of them have the same flux in the core. Downside to this circuit is it's again got worse common mode current than this circuit had. These two coils are coupled together very tightly in this transmission line, and consequently the common mode impedance is not nearly as good as you'd like it to be. But it is a circuit you can build. And this, by the way, in a 50 ohm circuit, this does not need to be a 50 ohm transmission line. It could be 100 or 200 ohm. This circuit right here is probably a 200 ohm or 300 ohm transmission line with these wires shown being separated somewhat. Do not confuse this circuit with this circuit. This circuit, the generator drives the voltage on one end of the transmission line. We take the output on the other end. That's different than driving shield to shield on this winding and taking the output from center to center. So in this case, we have pretty good common mode impedance because it's the impedance of this inductance that you get, or this impedance that you get by winding that number of turns around the core. And we have a better, but not great, replication of whatever impedance out here appears back here. And if we have a short length of transmission line, it's very, very good. As the transmission line becomes longer in this circuit, we need to have either a known impedance out here, say 50 ohms for 50 ohm transmission line, in order to get the generator to see 50. But this is generally a lot easier to do than these circuits, in my opinion. And this circuit has a couple really nice characteristics. And one of the nice characteristics is that it's pretty easy to wind. It has a real nice characteristic in that the coefficient of coupling between the coils is non-existent. There are no coils. So we don't have to worry about how much inductance we have here to mess with our generator impedance. So you might say, well, this is the classic transmission line, Balun or Unen or whatever you want. And the answer is yes, it is. However, this has flux in the core still. People a lot of times will make statements like, well, transmission line transformer has no flux in the core, therefore it's great. You can use a small core. The only size core issue you have to worry about is getting the wire through the center. And nothing could be further from the truth. In this circuit right here, if I connect point C to ground, there is no flux in this transformer to speak of. If I connect point A to ground, we see a voltage. Well, connecting A to ground, we see a voltage from here to here of the generator voltage. This sees a common mode voltage across the core of the generator voltage. If we connect B to ground, we see 1/2 of that. So if we assume that most of the time we're using this as a Balun, this circuit sees half the flux in the core that these circuits see. However, half is not zero. And I'll get into this in just a little bit. We'll do a little bit of an analysis. But before we do that, let's look at something real quickly here for SimSmith and modeling. If we have 3 cores that we want to wind in this particular order, these 2 windings, if you look closely, are wound the same direction. So that if I was to take this winding and slide it back this way, it would line up with this winding. The polarity, if I assume that there's a coefficient of coupling, in this case I said 0.77, if I assume that's a positive coefficient of coupling, then the phase dots would be here and here in my circuit. If I wind them in reverse order, then the phase dots are here and here for a positive coefficient of coupling. And if I wind them like I did originally, but I allow the coefficient of coupling to become negative, even though they're wound, this one is wound backwards from this one in terms of the order around the core. The phase dots go here. We will make use of that a little bit later in a circuit I'm going to analyze. And SimSmith allows you to have a negative coefficient of coupling, which does not exist in the real world, but it does act to turn the winding around is what it does, which is a really nice feature. Before we analyze the difference between circuit 3 and circuit 4, I'd like to make a real quick comment. If we look at circuit 4 here, we see that the impedance at this end, as reflected back toward this direction, is affected by the differential impedance of the coax. And the choking is affected by the impedance that this number of turns represents on the core with this length of coax, or the common mode impedance of this structure. This one is almost exactly opposite. If we look at this, the shunt inductance is the same thing as we see over here in common mode impedance. The common mode impedance of this circuit, though, looks very much like the differential impedance of the coax. The differential impedance of the coax is a low value, which is why I've predicted that this circuit will have really poor common mode characteristics when used as a balun. So let's go analyze that real quickly. So here's a circuit, 50 ohm load, 50 ohm generator, and a piece of transmission line used the way circuit number 3 used it. It's the same piece of transmission line. Matter of fact, it's the same circuit I built before with even though my drawing showed 7 turns, this circuit actually has 9 turns on it. But it really doesn't matter how many turns it has or anything else to show the point of this. What we've got is we have a length of transmission line. It has an impedance, velocity factor. We have a load, resistance out here. We have a tap point on it on a potentiometer, and it's in the center right now. And instead of using the file for the data values here, I used this inductance. It's pretty close at this frequency to being the same as the file, and it really doesn't change the problem. It just happens to be the way this just happens to be the Smith chart. The SimSmith file I loaded. What we see here is an SWR from 1.8 to 30 megahertz is not too bad. But we see common mode current here that's pretty high compared to our differential currents. And as we change the impedance of this transmission line to be a lower value, notice our SWR gets better, but our common mode current gets worse. So that's going in the wrong direction. If we go the other direction, make the transmission line impedance higher, what we start to see is the common mode current gets better, the SWR gets worse. This starts to look like the two coils not with 150 ohm transmission line and differential impedance. These two sides are not coupled together nearly as well as if it's a lower impedance. This starts to look like the first circuit we saw before, where it was just a transformer. It was had windings on one side of the core and the other side of the core. So this circuit has got this kind of a dilemma. What impedance transmission line should you use? I just said 50 seemed like a reasonable value, so let's just leave it at that for now. But we're going to compare this circuit with exactly this circuit if I take this structure and I just turn it 90 degrees. And that's this next graph. And all of a sudden we look at this one. It's got better SWR, it's got lower common mode current, it's got everything better. And it's the circuit that we know typically as a transmission line balun. So this is a reasonable explanation as to why most people do not use flux type transformers in these circuits, although there are people who do still. But you let the results that you see dictate what you'd like to build, of course. And SimSmith can help you along the way. Again, if you do build this circuit, you'll come up with different answers than I come up with, but the same general trends will exist. You might measure this current to be slightly different than I measured it, and your winding techniques and everything else will be different than mine. But nevertheless, you would probably come up with exactly the same results that I came up with. And now for the final circuit, as I had promised, some kind of an explanation as to why some people claim that a 4-to-1 balun done with transmission lines can or cannot be put on a single core. The classic way of doing it is to put it on two cores, and I've shown this circuit here where these two cores, I've got one transmission line here, one transmission line here, choking impedance across it. I've put a capacitor across that to represent the fact that this choking impedance has a resonant frequency. I've coupled the inductors together. It's shown right now with no coupling, so effectively they're two separate cores. This side, the two pieces of transmission line are driven in parallel. This side, they're in series. Equal delay through them. Should have good broadband characteristics. 50 ohm impedance here, 200 ohm impedance here, 100 ohm transmission line here. We could switch the circuit around to be 50 ohm here, 12 and a half ohms here. We'd have 25 ohm transmission line. And if we did that, we would be going the other direction. Instead of 50 to 200, we'd be going 50 to 12.5. But anyways, we can do all this. And we find out when we do this circuit that to get our common mode current lower, we might need these choking impedances to be higher because there's two circuits that are kind of in parallel here. But let's dispense with that. And I'm using roughly the same numbers I had before. I increased the inductance, I think, to 16 microhenry on the model I built. Just happened to be the cores I used and the number of turns. And let's put that in the center. 100 ohm transmission line, same 1.4 foot length I used before, velocity factor 0.7, it was RG316 Teflon coax. No coefficient of coupling between these two coils, indicating that these might as well be on separate cores. And this is the circuit I get. So let's look at what this is. The blue trace in the bottom is SWR, plotted from 1.8 to 30 megahertz. 1.8 to 30 megahertz. Very nice SWR, rises a little bit at the low end. That's okay. Still good SWR, still only a little bit over maybe 1.25 to 1. These three curves represent the two differential currents that go to the antenna. They're no longer 2 amps, they're 1 amp because this circuit doubled the voltage and halved the current. Still 100 watts here, being forced into here with a matching network. 100 watts will end up being here unless it's lost in heat in this structure. This 100 watts here, though, will now be 100 volts and 1 amp, which is, again, our 100 watts. So what we see is we see a current here of about 1 amp for our differential currents, and we see our common mode current being somewhere around, I don't know, 100 and, hard to say exactly what it is, 100, maybe 115 milliamps. It's a little bit more than 1/10 the value of our differential currents. Up here we see voltages, and I plotted them on this scale over here. We see the green and the black represent, let's see, let's turn those off and look at those just again and we'll talk about what they all are. So the green, which is from 3 to C, it's this point, from 3 to the center is across this transformer. The voltage from 4 to B is here to the bottom. That's across that transformer. So the green and the black represent the common mode voltage across this core. The orange and the green, the red and the orange represent the common mode voltage across this transformer. This transformer is not being stressed nearly as hard as this one is. The core is not being stressed as much, and that happens in lots of different circuits. They're not equal. It doesn't really matter. What we got is about 12% of our differential current as common mode current. Now let's couple the two coils together. In the process of coupling them together, along with what I showed on that other circuit before, we can make this coefficient of coupling run from -1 to +1. When we run it from 0 to +1, these phase dots apply. When we run it from 0 to -1, it switches one of these inductors around. It doesn't matter which one it switches around, but it effectively switches them around. So let's go negative to start with here. And as we start to couple these, I'm sorry, I'm going positive. Let's go negative to start with. As I go negative to start with, I notice my SWR rising a little bit, and I notice my common mode current really getting bad. Matter of fact, if I go to a coefficient of coupling of 1, my common mode current is basically the same size as my differential current practically. So, or actually 0.9 it is on the one lead. So this is terrible. But when we go the other direction, here again, we're at 0, no coupling. As we continue on with light coupling between the two of these cores with the indicated polarity as shown here, watch what happens. My SWR starts to rise at the low end, but the common mode current drops. So there's coefficient coupling of 0.2. Continue to watch the green curve and the blue curve as I increase it. 0.3, 0.4, 0.5, 0.6, 0.7. Now this is interesting, because 0.7 is the kind of values you get when you wind these two transmission lines on opposite sides of the core. So if somebody was to pick the polarity properly and wind this transformer, they'd be pretty happy. Now they might want to add extra turn or two because the SWR is starting to come up here. And we could achieve that by just taking this circuit right here, and let's just bump this inductance up to say 20 microhenries. Now we've moved it down again, maybe 23, 24, whatever. Now we have good SWR and very good common mode current here. Common mode current's only 3. It's 1/30th of the value up here. Very good performance, single core. This person who did this touts how they can do it. And then another person comes along and they have this coefficient of coupling and they say, you can't do it. I believe this is much of the reason why there's such a controversy about whether you can or can't. It's determined by what percentage of coupling you actually have. And I've seen this before in some other stuff. I did some work on some low-pass filters for an amplifier one time, and I wanted the filter to be fairly small, so I had some coupling between some air-coupled coils. And it turns out if I oriented the air-coupled coils properly, I could get very little current, very little coupling between them, which was good. But if I oriented them so I had a little coupling and it was the right polarity, the performance of the filter actually increased. I got better roll-off. And we see that a lot. Sometimes some inadvertent coupling helps you and sometimes it hurts you. And here's a case where we've figured out a way where it helps you, and we've also seen where it hurts you. Hopefully this has been interesting. There's a lot of information in this video. It's probably longer than I'd like it to have been. If anybody gets to the end here and enjoys this last section, let me know. Some of these things that people tout about being hard and fast, that thou shalt not do, and that you must do this all the time. The rebellious part of me says, I really want to know why and try to figure it out. In a lot of the cases, there's reasons for this stuff. People reiterate what they've learned in the past. They've seen some evidence of it. They're not trying to deceive you, but this whole story is not also being disclosed. So hopefully this has been enjoyable. I certainly have enjoyed doing the video. I don't know if anyone will appreciate it because these topics are starting to get to be pretty complicated topics. But nevertheless, they are enjoyable to some people, I think, and I've learned a heck of a lot along the way. 73, W0QE.